Should we get started? Okay. Yeah, it's a great pleasure for me to introduce Joaquin Camacho. Um, Joaquin is at San Diego State University. He's an associate professor. Actually, he started out in he did his bachelor's here at UC San Diego, and he worked in the combustion laboratory, did temperature measurements and flames, radiation questions, and from there on, moved up to University of Southern California, where he worked in Taiwan on combustion, and moved with Taiwan over to Stanford, and he was a postdoc as well. So today we're going to talk about a very interesting topic on the formation of graphene nanoparticles, high temperature premix flame.
Thank you very much. Yes, I'm very happy to be here. And yeah, so I was here as a chemical engineering undergraduate. And back then, Professor Shashadri and Williams were involved in classes there. So I took classes with them as well. And I'm using my chemical engineering background for this chemistry, the transport part of this. And like, for example, on I guess I have to use my hand here. Oh, so, well, it should work then. So, okay. So yeah, so carbon soot is one of the many infinite forms of carbon, and carbon is known if you were to expose some solid carbon materials, it would anneal to get more and more crystalline as the temperature increases. And soot is not necessarily, it has some crystalline structure, but lies more on this turbostratic or less orderly, less than graphite type structures of carbon. And you would assume that if soot were exposed to higher and higher temperatures, it would follow a similar crystalline structure behavior as well. And so what this project that I've been working on, is working on the hypothesis that traditional combustors, engines and planes, and other industrial combustors, they try to avoid high temperatures for emissions reasons and other reasons. They typically operate much lower than 2000 Kelvin. But newer, high temperature combustors and maybe emerging applications like kerosene-based rocket engines, they operate at higher temperatures. So if they do indeed burn hotter than 2000 Kelvin, and they do produce this soot, which is indicated by a yellow color, any flame that you see with a yellow color, there's carbon nanoparticles emitting black body radiation. So this is what we're seeing here. And if this flame was indeed high temperature, then and in these new applications, then maybe we would have a type of carbon structure different than soot, and that's different than it has more crystalline structure and unique properties. And this has not really been studied. And so, see if I answered today, I'll talk about a specific flame configuration that I've been focusing on that you're able to access higher temperatures and produce these structures, which is relatively new, but I've been developing more and more experimental evidence and hopefully more modeling and chemistry and physics behind what these processes. And the experimental methods I'll focus on today is a high resolution microscopy with transmission electron microscopy, Raman spectroscopy, X-ray flow electroscopy, and a way to measure the subparticle size as it comes out of the flame in the aerosols. It's still following the gas phase flow. And today I'll focus on experimental results showing evidence that indeed we do see a transition where at lower typical flame temperatures, you see soot-like structures, and as you increase the temperature beyond typical flames, you do see graphene-like structures. And I'm also working where we are now is trying to look at go in the steps before soot even forms, the precursor chemistry of the flame that would lead to solid particles, and focusing on this regime of high temperatures. So the flame that I've been focusing on is actually what I got started on here at UC San Diego, counterflow related flame, where it's a stagnation flow. So it's a stagnation flow, but instead of being a pulse flow with two jets, it's a stagnation flow with one single jet impinging upon a plate. And this is a very nice flame academically because it gives you a relatively well understood flow field that allows you to explore other phenomena, flame phenomena or flame chemistry phenomena. And as a matter of fact, the formulation that Professor Williams and Shashari have been working on for a long time is using this counterflow type flow field and using an assumption. Actually, von Karman was credited with first introducing a similarity solution where you can reduce this axisymmetric 2D flow field into one dimension effectively. By making some assumptions of having a nice wide aspect ratio, and you can combine the radial velocity with the axial velocity if you assume this linear function here in R. And without not a lot of details here, but by applying this formulation, you can get a relatively simple flame structure calculation in one dimension and able to get the velocity fields in 1 and 2 dimensions, and the species profiles and the temperature profiles. So I'm not going to focus on the modeling results here, but the experiments are pretty good. The experiments can be described pretty well by this relatively simple flow computation. And it also allows you to give you a relatively well precisely defined temperature time history, which can be useful, to get more systematic in terms of the physics and chemistry going on inside the flame without complications of turbulence and other high dimensional behavior. Yeah, these will be the boundary conditions. We have a stagnation plate here, and we can measure the temperature there. So that'll give us the temperature, assuming the bulk velocity is 0 at the plate, stuff like that. It's a relatively simple flow field to use. And previously, we're showing that, we have showed that this flame was already known is that this flame stabilization mechanism does not depend on heat loss flame anchoring. Because of that, it burns hotter than other laboratory flames. A Bunsen flame, burner stabilized flame. This one is stabilized here at this steady position due to aerodynamic kinematic balance. Because of that, there's much less heat loss, and we can burn hotter. And if we apply this computational model, it would predict that you're burning at about 2,200 Kelvin or so, according to the computation. And we're able to take measurements based on the black body radiation that indeed we are much hotter than typical flame temperatures. So this flame is very nice to give us a nice, relatively simple flow field with flame temperatures much hotter than typical flames. So that's what I've been using to look at the particles forming. So there are particles here, and this is black body radiation of solid aerosol. And we're going to look at the differences between soot formed in this regime, high temperatures, versus typical flame conditions. So given that, what the actual soot formation process is a specific gas to particle transition, whereby if you have fuel-rich conditions in the flame, it could be non-premix or premix, but as long as there's some pocket where there's a lot of hydrocarbons, what will happen is if the temperature is high enough, it'll either break down or it will build itself up again. It'll build itself up into these aromatic precursors, and at some point, these aromatic precursors will transition from these gas-phase species at high temperatures into a solid particle at high temperatures, starting from like 1 or 2 nanometers. This transition occurs at very, very small scale, almost molecular scale. And then if we're looking at this as a one-dimensional progression here, which is hard to do in a real flame, but in a laboratory flame, you can systematically study how, as you progress from the flame to formation of carbon soot precursors, you grow in size. And then once you have this transition from the gas to the particle, there's a lot of processes where these particles grow. And what the traditional soot formation process in traditional flames, at typical flame temperatures, the structure is known to be it has some crystallinity, but not very sharp crystalline structure and not orderly crystalline structure. It has this turbostratic, meaning it's kind of this, it has some layers, some orientation to it, but it's not straight graphite layers. So this has been studied for a long time in terms to help aid soot formation research, which leads into cleaner burning engine, to try to avoid emissions and things like that. So when we have these higher temperature flames, we should indeed expect that the structure of the particles, the material, the carbon material itself, should have a different crystalline structure than typical soot. And if it's high temperature enough, perhaps it will even evolve into this graphite, graphene type structures. So experimentally, we'll look at these characterization methods, like for example, Raman spectroscopy is very useful for carbon materials. And what Raman spectroscopy does, it just shoots at a photon at this material, and it doesn't. It's a surface weighted measurement, and based on the response of the phonon modes or the material properties, it'll shift the light by the Raman process. And what you're measuring is the shift in wave. I should say Raman shift here. Wave number that indicates a shift in the light as a response to the vibrational modes of this material. And carbon is very sensitive to this. And as we know, carbon is a wide spectrum of infinite structures. It can be just sp3 diamond type bonds. It can be totally amorphous, or it can be very crystalline structure sp2 bonds, and everything in between. And Raman is known to be able to capture all of these things depending on the structure. Soot formation research has been studied in great detail using high resolution transmission electron microscopy. And here's a classic example, or like one of the foundational works of Van der Waal, where he was able to, one of the earliest works demonstrating how you can use image analysis to systematically quantify the structure of soot. So here's a picture from this paper here, where it just studies engine soot, and a typical structure that's now present in many other subsequent research on soot formation. And so this is the turbostratic structure I was mentioning for soot. It has this core shell. It looks like an onion. And for the last decade or so, researchers are quantifying this in terms of the distance of how straight this lattice is, and how distance between this lattice. And what's interesting is, yes, it does help to develop some of the models of soot formation and how these grow and engine conditions and things like that. But you have to be very precise, because there's not a lot of variation. This is pretty much represents all soot in all conditions, or all typical flame conditions. There's not a lot of variation in this. And what I'll show is the particles I'm forming are drastically different, a completely new regime than typical soot and combustion engine research. Another very useful technique is X-ray photoelectron spectroscopy. It also focuses on the surface, but what you can get from this is, by shooting these photoelectrons at the surface, you can get at certain you can keep track of the energy you're putting in, and then it'll shoot off an electron, and that will give you the binding energy. But in terms of soot, what we use that for is to determine the amount of sp2 bonds versus sp3 bonds, like double bonds for graphite versus sp3 like diamond-like or amorphous. So this XPS measurement gives you an idea of sp2 carbon bonding versus sp3 carbon bonding, which is very useful for studying crystalline structures. And the soot in this flame is a aerosol that where particles are following the bulk gas flow. And another measurement I'm using is to sample the flow of the aerosol. The particles are still flowing in the gas. And if you expose it to an electric field, you can classify or separate a mixture of different size aerosol particles into one single size, depending on the electric field, taking in some assumptions on the drag force, balance between the drag force in the flow and the electric force on the cold flow. You can separate these different sizes out. And that's what I'll use. Specifically in this 2 to 60 nanometer range, very small, finest of the fine nanoparticles. This is pretty much molecular scale here, but this analyzer, where it's able to separate and measure and count them to get a distribution. So in terms of sampling this plane, we have a stagnation plate where this flow is impinging on as a counterflow at the stagnation flow. And we can have a sampling orifice in there where we can dilute and pull some of this flame gas out. And what I've done is feed it into this aerosol analyzer to get a size distribution. But also downstream, it's a diluted aerosol. I also use this to deposit onto a TEM grid to get a sample under the microscope of the structure as an aerosol, depositing onto this grid diluted downstream. So that's one measurement I'll present. Another measurement uses a different sample collection technique. It's just a direct deposition of the particles on this plate. So we can just mount one of these plates on there, and over time it'll grow a film just as a stagnation surface. It's a chemical vapor deposition, but instead of the gas phase precursors growing into a film, it's just particles sticking onto the film to form a porous film. And we'll analyze this. And also another method used to look at these soot particles is this is a typical very small sample holder or sample substrate that you put into the microscope. So what I did is to get particles for the microscope, you simply just rapidly insert this in and out of the flame. And by doing that, the relatively cold surface going into a hot flame will induce a thermophoretic force, and it'll stick onto this very quickly. And you can look at the particles that stick on there. So and what we'll actually see is that the particles observed under the microscope are different in each of these cases.
Even next time you do it, you get a different.
No, yeah, there's some. It's rare, like yes, there's a wide variety that it's not the perfectly same reproducible structure, but I'm saying that and if you collect a particle from a diluted flow downstream, it'll look more amorphous sample. If you look at it here, we get a lot of crystal artifacts, and you get more soot. Looks more, we're probably having soot in the flame. And by having these deposition processes over time, I'm thinking there's like some CVD type growth processes over time that are not flame processes. And yeah, so sampling, the way you sample this flame makes a difference in the products you're observing.
You haven't told us anything about what the fuel is or what the fluids ratio is.
Yeah, so the fuel, I didn't mention the fuel. It is ethylene in every case.
Well,
ethylene, just a nice simple fuel that readily produces soot. And the temperatures are in the range of 2000 Kelvin to 2200 Kelvin. And the covalence ratio, here's two examples I'll show. Relatively high.
Oh, there's the equivalence ratio.
Yeah, and what's interesting about these flames is that if you have keep the equivalence ratio constant, like a typical equivalence ratio where you'll see flames is 2, meaning that you have twice as much fuel than you need. Like 1 would be perfectly balanced. So 2 would mean you have twice as much. Typically, that's where soot starts to form. You have twice as much excess fuel, you'll start to form soot particles. And I'm much more high than that. And the reason is because if you keep the flame temperature, if you keep the equivalence ratio of 2, but the flame temperature increases, the soot production will decrease. Because as the flame temperature increases, the precursors are less favored to grow. They kind of fragment rather than grow into soot. So for me to see soot, there's not a lot of soot in there. For me to see it, I had to jack up the equivalence ratio to have a lot more excess fuel than normal. And I think that's why I'm seeing deposition results, because there's so much excess hydrocarbons in the flow. It kind of evolves into a CVD process if you collect over time.
Ethylene in air?
Oxygen, argon.
Oxygen, argon.
Yeah. So similar to air, just I like argon because of the heat capacity effect. Argon flames are hotter. So I'm trying to get high temperatures. So the nitrogen.
That's how you achieve such right.
Yeah, that's one thing that helps. Yeah, it gives more wiggle room because the air, air or oxygen, nitrogen would be colder.
Yeah.
Yeah.
Good adiabatic temperature. It's not really that.
Right. Right. Yeah. So these are argon. Yeah, I didn't leave those details out, but I guess some people would know the importance of these things. I didn't focus on a lot of the details. But yeah, so here is a Raman spectrum of this film here. Over time, it takes time because at these high temperatures, there's not a lot of soot yield. So it'll take time for this film to grow to get a signal from this film. So this is taking a film, going under the Raman spectrometer. This is the signature we get. And if the flame is 1900 Kelvin, what we see is a Raman spectrum typical for soot formation. Like this is a lot of soot formation studies on Raman go into a lot of this intricacies of, this is the D response of carbon to these Raman ship. And this would be a perfect graphite peak. If there's nothing, only graphite crystal, you would only get this peak. This is kind of some disorder imperfection peak. And then there's these other amorphous things that you can put a lot of, quantify a lot of the structure on. I won't present that there, but the overall structure the signature looks like soot formation. But interestingly, as we keep the equivalence ratio the same and increase the temperatures of these flames and look at these films, what we get is an evolution where at higher temperatures, the Raman signature changes. As a matter of fact, this is not soot anymore in terms of the Raman spectra of the film. Soot researchers, looking at Raman spectra of soot, no one has reported a structure like this. As a matter of fact, if you go and see what this corresponds to in terms of literature and predictions of the theory, this is graphite. This is graphenic type materials. It's not perfect graphite. Perfect graphite will only be this, but it's some type of disordered graphite material according to the Raman spectrum. And this is the high temperature, clear evolution from typical flame temperatures or more on the high end of flame temperatures going to even higher. We do see that the film grown is much different than soot. That's a first evidence. And so yeah, this is the evolution. And again, you can do some analysis, and according to the literature, you can makes a lot of reference inferences on the structure based on these peaks and things like that. And I have done that. I didn't put the reference here, but yeah, a few of my papers are looking at this analysis. And then continuing with XVS, by growing these films, looking at this binding energy under this XVS, we can take some assumptions, typical analysis on XVS. We can say that for a flame at 2260, at this high equivalence ratio, a little bit lower, you have 75% sp2 bonding versus 62% bonding, which is much higher than soot formation. As a matter of fact, so-called hard carbon, which is a important carbon for batteries and energy storage materials, even this hard carbon has 47%. So in both, carbon used for energy storage applications and soot, there's much more sp2 bonding in these films from these high temperature flames. So reminding us on these measurements I looked at high resolution TEM by growing this from a diluted flow, collecting film or particles from a diluted flow, connecting these films over time from this deposition surface, and a rapid insertion of this TEM grid. We see graphite structures, graphenic nanomaterial structures, but there's a lot of variation depending on the how we collect it. So here is a microscopy picture, low magnification, to try to get the particle size distribution of a high temperature flame collected from a diluted flow. And over time, these particles indeed stick to this microscope substrate, and we can get an idea of the size distribution, just count them and get a histogram. And also, here's another type of measurement technique where you probe the flame, dilute the flame, and feed it into this aerosol analyzer. It will classify the sizes by the electrical mobility, and their overall agreement is good in terms of at this equivalence ratio, the median diameter is 6 nanometers. At a higher equivalence ratio, you get bigger particles, and that's corroborated. I didn't put the numbers here. I should have. We counted these, and there's good agreement. But so this is showing that we do indeed have very small nanoparticles, almost molecular scale nanoparticles at the earliest stages of growth, right when they transition from the PAH into a solid particle. We're able to capture them on the film or analyze them from a diluted flow. So these are very small graphene type or very small carbon nanoparticles. And then interestingly, looking at higher resolution images, it's not the same uniform structure of carbon materials. We actually see a lot of amorphous structure of particles. So here's like one example. If you go across this whole sample substrate, you have these big blobs of pretty much amorphous materials. There's no crystal structure there really, but in some areas there are crystal structure. You see these strands of graphene rivets basically. So this, if you look at this distance, measure the distance between these fringes, that fringe is the graphene layer, graphite layer distance. So this is one evidence of the graphene structure. Very long length of its fringe, which is much longer than soot particles. Soot goes into this onion shape. It's kind of curvy, tortuous structure. This is in this particular area, it's just a big, straight kind of graphene ribbon. And then if you go across the areas, you'll see different examples where there are some amorphous structures, but there's definitely these distinct, this is not soot, this is graphene ribbons here. And it's not a complete, clean, uniform structure of graphene ribbon, but it's clear that it's there, and it makes sense of where this Raman spectra came from. There's probably seeing this crystalline graphene sheets that give the Raman response that I've seen earlier. So that's what an example of this TEM images under this diluted aerosol sample. And here's even more, that this is clearly not soot. Soot would not be as transparent. These are like graphene, very small graphene clusters or graphene sheets. And this particular sample collection method is relatively transparent. You know, the contrast is not great because it's so thin and few layer graphene. Because of course, graphene is one layer. You have single layer, two layer, and then few layer. So this is like graphene of a few layers, not more than 10 or so like that. Very transparent, not soot. And then taking another measurement technique, taking the film that we collected over time, you know, scraping it into its powder, and then drop casting it onto a TEM grid, we see a similar result, but it might be even a little more crystalline. And there is definitely similar evidence of this graphene-like structure. So this here looks like a little bean, you know, with this more uniform structure, and you know these ribbons observed. So this is not soot, and you know this. It's hard to avoid these things from coagulating because it is a powder that deposits, and then when you try to collect it, disperse it into a droplet, and then coat a TEM grid with this, it dries up, and then as it dries, it coagulates. It bunches up again. So it's very hard to disperse these. But nonetheless, you do see clear, straight lattices, unlike soot. Here are more examples. Like this is not soot; it's just graphene type materials. Yeah, and the goal. I'm still working on ways to make better samples to get these more dispersed, to get more details of the particles rather than the clusters, because they're the time and the conditions we have, they're not forming these big, what is this, like 100 nanometer aggregate agglomerate. That's not happening in the flame. It's just when you prepare the sample, they just coalesce like this. Okay. So another sample collection method we used was to insert rapid insertion of this TEM grid so that we can just collect, dip in and out, and it should coat the substrate with particles. And indeed, we did get these particles, and it's probably what we're observing in the flames. This orange color is probably these typical soot particles. So the particles that are flame formed, naturally born in the flame, it's probably soot. That's what this structure is. Aggregate fractal-like structure with this turbostratic-like structure. It's no longer these straight graphene layers, but this is typical of what we see for soot. And when we do this rapid insertion directly in the flame instantly, we do capture evidence that it probably is soot forming in the flame. But then when we collect over a longer time, we probably see graphene structures that occur probably from like a deposition process over time with them, because there's so much excess fuel, extra hydrocarbons in the flow. as you deposit over time, they undergo a different process. That's not flame aerosol process. Okay, so we also see a lot of artifacts that when you rapidly insert into the flame, it's some rapid condensation, quenching process. I'm thinking that this is typical soot, you know, these little soot particles. This is what we are expecting for soot formation. But we also see this huge structure here, and zooming in, it becomes, it's graphite, basically graphite. And even this little pyramid structure here. And it's definitely not forming in the flame. It's probably an artifact of excess hydrocarbons being quenched by the surface and depositing, and maybe even growing as you pull it out. You know, it's like a liquid when it's in the flame, and as soon as you quench it out of the flame, crystallizes into some structure or something like that. So there's a lot of work we are yet to do to organize these, separate all these competing processes. But one thing is for sure, this high temperature, high equivalence ratio flames give a unique regime whereby this particle, the carbon, you can get is graphenic, depending on the conditions, and you even can get these artifacts in there as well. And yeah, some more examples of these graphene-like graphite structures can be observed. So to summarize this part, they stretch stabilized flames are high temperature, and if you want to get soot formation at these high temperatures, you have to go to very high equivalence ratio. That offers a unique situation where I think we observe like both soot formation in the flame and deposition of anything from amorphous to graphite structures, depending on the specific condition. And there's a lot of work to do to separate all these competing processes. And there's a mixture of graphenic, amorphous, and typical soot. But definitely there is, this is evidence that these high temperature flames are, give you a different regime than typical soot formation. So I was doing work to quantify all of these competing effects. And so that's.
Like, you explained it all in the fifth strain rate, right?
I guess not the same. It's both. We changed a lot the velocity of, yeah, it's not necessarily the strain rate. I guess we do keep the distance the same, but the velocity changes. It's, yeah, we try to keep the growth time the same so that you know, it's a similar, even though we change the temperature, we try to keep the time the same, and that changes the strain rate. Yeah, because the flame moves depending on the, let's set a picture of it. Yeah, depending on if what the temperature of the flame is and the distance is, the flame moves, you know, within sugar rate. Yeah. So yeah, so the strain rate's not okay. Yeah. So another work to help to, I'm very interested in eventually showing that we have interesting materials and maybe even find applications for these graphenic materials. But a big interest is also understanding the chemistry, physics of what's happening and how to the fundamental processes leading to these processes. And this is a gas precursors. So another area of research that needs a lot of work is this precursor chemistry. They're called polycyclic aromatic hydrocarbons. There's still a lot of experimental measurements that could be made to help the chemistry, kinetics of these precursors and the transition into the particles. So another area that I'm starting, which is very early progress, is measuring and quantifying the concentration of these precursors in the flame. So the chemical species measurements. We use this dilution probe, the same stagnation plane with a probe that will allow us to pull a diluted sample and hopefully quantify the concentrations by gas chromatography, mass spectroscopy. And I have some preliminary computations of these flames using these specifically flame chemistry models focused that have this aromatic chemistry in it. There is a few of them, but I focus on, you know, this is a good starting point. It's one of the oldest models, well developed for detailed chemistry, an Apple Bockhorn Franklin model for pH. And then out of Kaus, they have this very comprehensive flame chemistry model with pH. This should be pH, but it's another one from Stanford, Blancard, FEO pitch for flame chemistry, flame chemistry and pH. So these are three models I have computations for, and hopefully we can soon quantify experimental measurements to compare. And what's well,
There's so many unknowns in those models.
right? Yeah,
None of them are right. Let's face it.
yeah. So going ahead, that's what the measurements show, that not only is the prediction temperature and condition dependent, but the prediction is model dependent. Yeah, so hopefully experimental measurements, there's not enough experimental measurements to constrain them. That's the challenge. And hopefully I can help to produce experimental measurements to help the modelers insight into what's happening. All these assumptions that have to be made due to lack of experiments to help guide and constrain. Yeah, so what we do is this pH, there's some challenges that go into taking these measurements, because in the flame, everything is the precursors we're interested in are gas phase. But as soon as you take them out of the flame to normal temperatures, the heavy precursors, they condense. The big molecules that were gas phase in the flame, they condense. That can cause problems because a measurement that would work for smaller gas species like CO2, hydrogen, and water and things like that, it'll work fine just by simply directly feeding a line into an analyzer. Or in my case, I took a sample cylinder, collected a sample, closed it up, and then feed it into the GCMS, the analyzer, in two steps, collect, then carry over to the analyzer, and then inject and analyze. That works relatively simply. But if you were to try this technique with like naphthalene or pyrene, or even benzene in my case, these species that condense at room temperatures into liquids, you would lose your sample. It will not stay in the gas phase unless, so you risk either losing a lot of the sample or completely losing it to wall loss it'll grow a film on your cylinder. So what we did was had two experiments, one for gas phase species, and then a separate one using this condensation behavior to accumulate condensable species over time. Over time is important because these condensable species are gas phase in the flame, but they're also much lower concentrations, orders of magnitude lower concentrations than the CO2, CO, water. These precursors leading to carbon and soot are orders of magnitude smaller concentrations. So it takes time to accumulate enough. In my case, I have a relatively insensitive detector. If I had a more sensitive detector, it would be easier. But this is not as sensitive, so it takes time to, over time, condense this onto a metal filter cold trap. We just simply pass this flame sample over this trap at a cold temperature over time. And then what we expect is that metal filter that we can dismount and inject into some ultrasonic bath to shake it up and extract them from the surface of the metal into solution. And then when we have a liquid solution of sample, we can inject it into analyzer. So this is two methods. One just for gas phase, anything that stays readily at gas phase, and others larger molecules that condense at room temperatures. We use that condensation to collect it over time, and then hopefully extract into and collect it into solution and inject the liquid solution. So, and then as we just discussed, the models are lacking experimental measurements to help to constrain them, especially at this high temperature. I just said that this high temperature regime is most combustors, most engines try to avoid these temperatures, but I'm trying to focus on these temperatures. So I'm extrapolating existing models even further to their comfort zone. So that's a problem. It needs experimental measurements or some way to constrain them more. So even for these radicals, you see this almost an order of magnitude difference between just a precursor to benzene. And then once you go to benzene, there's another order of magnitude discrepancy between them. at this range of temperatures. And yeah, so if you go to a bigger naphthalene, which is the next stage of growth of these PAH, you have a huge discrepancy between these models. So hopefully these measurements that I'm still working on, I haven't quantified them yet, is to help to constrain them and see who's right. Maybe I'm the only one right. I don't know. So yeah. So yeah, we have qualitative, well, the gas phase, we do have quantitative measurements of the gas phase. So what you do is you feed this into the gas chromatograph mass spec. And what the gas chromatograph part does is it separates a mixture. So this is what we get from the gas chromatogram. It's you feed it into this chromatography column, and over time, each of these molecules separate, and then it detects each one as they come out. So it detected that we have some hydrogen coming out early and some nitrogen CL. So these are the species in the gas phase that we can see. And we have since quantified these in terms of our calibration. But the challenge we're having now.
O2 there. It's interesting.
Oh, right. The O2, it's very hard to quantify that from this method because you have.
You don't have O2, but
Oh, yeah.
Oh, right. Comes right next
Right.
to
It is, it probably would be in fuel lean flames. And it probably is there as some noise peak because it's very hard to get this from leak proof and like any if we do CO2, it wouldn't be from the flame, it would be from the contamination.
Yeah, it's very little O2 in your slide.
Yeah, right. Like it wouldn't be from. I would see it. I do see it sometimes if we have leaks. Yeah, it's very hard to avoid the O2, but it's not from the flame. Yeah, and you're right. It is somewhere here. Yeah. Yeah. Um, yeah, here's an example where we did manage to eliminate leaks from the O2 that can, it would be contamination in these claims conditions. And yeah, so this is gas phase. We have quantified this, but our challenge is the condensable cold trap method. We are successfully able to capture and see that indeed, yes, this flame has xylenes. This is a so toluene has one methyl group. It's a benzene with one methyl group. Xylenes are two methyl groups at different positions. So we're able to see those. Those are important precursors. And then we can even see the larger aromatic structures like this. Forget the name of this. It's not acetonephthalene. This is acetonephthalene 3, and then this is this 5-member ring here. You do see these condensable species that collected over time. It's just been a very big challenge to quantify precisely the relationship between our dilution, our deposition, extraction, translated into flame concentrations. That's what we're working on calibrating right now. And our approach is to maximize the signal. By maximize the signal, we can decrease the error. And then, by the way, this is a signal to noise ratio problem in this result I'm presenting here. Is that we do see species that we know is from the flame, but there's a lot of other peaks from the gas chromatography column itself. Like if you're able to have a big signal, strong signal, you wouldn't see this noise. But we're at the level of noise because there's materials in the column that give off these signatures. And it's just unavoidable signatures of noise. And if you had a large signal, you wouldn't worry about it. In our case, our signal is not too strong. We do see a lot of noise. So we're trying to increase the signal to noise ratio, and then quantify, calibrate. That's where we are now. And hopefully by doing that, we'll be able to constrain the models, which are very lacking in terms of constraints. Okay, yeah, to summarize this part, we have this flame probe sampling method to both study gas phase species and condensable large molecules using 2 different measurement techniques. And we're further work on quantifying and calibrating this process. And yeah, so going back, the whole goal is just to study this fundamental processes. We have shown the particle properties that are indeed different than soot. There are many different types of carbon, including graphite and graphene structures. And now we're interested in understanding the fundamental chemistry leading into these particles and with measurements of the chemical species. And hopefully eventually that would lead into applications. We have these particles, we know how to make a specific structure and then use it for a specific purpose because carbon, graphene, nanoparticles are very useful for many applications. Yeah, so with that, I'd like to thank everyone and acknowledge my lab. And this was funded by a career grant from the NSF. So thank you, and happy to take any questions.
Good.
Your questions, sir.
It's very interesting. It's very challenging. I guess those ones that you showed is from calibrating those structures you use to calibrate.
Yes, yeah, from calibrations, we can know the time that they come out of this condition.
Yeah.
So that gives the qualitative answer of what we're seeing, but the putting a mole fraction of the flame on it is the challenge that we're working on now. Yeah.
So what do you think are the precursors for this?
Yeah, it's kind of
how are you different from so?
It's probably the same precursors. What I'm thinking is that the growth processes after the particles form might be different. Or it might, when I do see a lot of extensive graphene structure, there might be a possibility that I'm probably seeing in the actual orange flame, it's probably soot. But then that sooty flame has so much more carbon that didn't form particles, it gives you the opportunity to have a deposition of graphene, like a CVD process afterwards. That's probably what's happening. It's probably a CVD over time leading to graphene-like structures. Yeah, from this excess precursor that did not form soot. Yeah.
Yeah, you showed those different PAH model predictions.
Yes.
You're going to be able to say one of them is wrong or the other one's wrong. Or like you say, maybe they're all.
Yeah, hopefully I'm right in between. I don't know.
Well, it'll really be interesting to see where your results come there.
Yeah, it's taking some time because I know how important it is to be able to be confident and put a good error bar around this based on a sound reasoning and things like that. Yeah. But yeah, this is order of magnitudes different here. And in this area of research for soot formation, both the soot concentration and the precursor concentrations, they're happy with a factor of 2, like plus or minus 100%.
Good.
That's a reasonable agreement in this area.
No, I see it certainly.
A factor of 10 is not.
Yeah, factor of 10, that's pushing it.
Yeah. So I see a settling here. So,
Yeah.
But you really show us settling on your.
Oh, right. I did not. Yeah, I do have a settling results. I do have results showing the comparison it's good. Yeah. For acetylene, for particle, it's not a stable species that we can measure.
Yeah, right.
But the gas phase species, it's a reasonable agreement. Yeah. I should have presented it. Yeah. Yeah, and this is not a flame profile. It's like a summary of the max species at one max temperature. It's kind of like a global summary to plot. Yeah.
Any other questions?
So no questions from Zoom, I guess. I don't see it. Yeah,
but stagnation flame, there is a code, right? ANSYS is the code on.
Yeah, ANSYS has a code that they got from Optiv code, the Sandia packages. ANSYS or Kimkin took that, and then ANSYS took.
In the stagnated the plate, there's no heat losses.
No, it is heat loss, but it's a water cooled plate.
So therefore you
Yeah, so the typical
you don't specify the grading the plate.
No, I just give the boundary, the top temperature and the inlet temperature and the exit temperature. And this will be a typical profile because in the experiment, it's a water cooled plate. So for a lot of the domain, it's pretty much close to adiabatic. And then it reaches the plate temperature close to the plate.
Is it that your measured temperature is appreciably higher than
Yeah, this I think. Yeah, like this 3000. Yeah, I'm pretty sure these particles are not. You know what it is? It's an optical. You have to make an assumption in the black body radiation of the particle products. And a typical assumption is this dispersion coefficient here. F1, that works okay for soot, typical soot, but I guess this is one of our arguments that this is not typical soot mating. So we did an independent measurement with this assumption, gets us much higher. But then we do a less independent, we do, instead of, we kind of hybridize, say that the optic gives us this temperature. So we fit this parameter here to give us a good agreement. So this is less independent measurement. But then, so the question is this a reasonable assumption or a reasonable values that we get, physical values? So they are physical values, typical of carbon.
Yeah, one could have believed those computed values, I think.
Yeah, right, yeah. It's these, oh yeah, the computer values, yeah. Yeah. Go ahead.
This might be a naive question, but like, do you think you can get the graphene structures before deposition?
Yeah, I think if the temperature is hot enough, yes, yes. And yet it might be a thing where you have to selectively push the direction away from soot particles forming and like more of like a graphene forming somehow, either through temperature and concentration. There might be a small sweet spot of equivalence ratio that favors graphene versus soot. Yeah.
I have a question. So when you want to, or when you plan to take some samples from lab, I saw that you use the use the GC and the mass
Spec, yeah.
yes, and to test the sample. So did you try to keep the high temperature during transport the species?
No, that can be important. No, what we assumed is that hopefully we dilute enough that it quenches and it stops any reactions.
Yes.
That's why we want to dilute. So hopefully by diluting it, and then time as well. If it's not an equilibrium sample that's in there, so over time it's going to equilibrate to something else. So we do try to be as fast as we can in transit, but we rely on our dilution to stop any other reactions. Yeah, yeah, but that can be important. Yeah.
Everybody else. Thanks a lot. Okay, thanks.
Well,
Okay. So,